Imagine teaching a child to recognize animals. You show them a cat, then a dog, and correct their mistakes. Over time, they learn the difference by spotting patterns. Neural networks work similarly, but inside a computer. They're inspired by our brains, made of interconnected nodes called neurons. Instead of being programmed with strict rules, they learn from data, thousands of examples, discovering patterns on their own. Layers of artificial neurons process information. The first layer looks at pixels, the next finds shapes, deeper layers spot features like ears or whiskers. The final layer makes a prediction. I'm 90% sure this is a cat. Each layer builds on the last, refining the network's understanding. Like a child, a neural network starts off making mistakes but learns from them. The key is learning through practice and correction. It needs a way to measure how wrong its guess was and adjust its connections to improve. This process, learning from errors, transforms a simple network into a powerful learning machine. Neural networks can tackle complex problems, recognizing images, understanding speech, even driving cars. The magic lies in their ability to improve with experience. We'll explore how they use mistakes to get better. This is the foundation of modern artificial intelligence. Let's see how a neural network actually makes a guess. When a neural network makes a guess, it's called a forward pass. Imagine it's trying to identify a handwritten number from a picture. The input is a grid of pixels. Each neuron in the first layer receives part of this information, like the brightness of a pixel. Neurons perform calculations and pass results forward layer by layer. Connections between neurons have weights. Strong weights mean important signals, weak ones mean less important. Hidden layers detect features like curves and lines. The output layer makes the final decision, say, picking the digit 7 inches if that neuron has the highest score. The network's answer is based on its current understanding, shaped by all its weights. At this point, it doesn't know if it's right or wrong. The next step is to compare its guess to the correct answer. That comparison is what drives learning. After the network guesses, we need to measure how wrong it was. This is done with a loss function, a mathematical way to score the error. If the network guessed 8 inches instead of 3, the loss function calculates how far off it was. A small error means the guess was close. A large error means it was way off. The loss function compares the network's output to the correct answer and gives a single error score. This score tells the network how much it needs to change. The goal is to adjust the network's settings to make this error as small as possible. Training is a cycle guess. Check the error and try to improve. The error score is the feedback the network needs to learn. Without it, the network would have no way to know if it's getting better. Now let's see how the network uses this feedback to improve. To improve, the network uses backpropagation, a way to send the error backward through the network. Starting at the output layer, it figures out how much each neuron contributed to the mistake. Using calculus, it calculates blame for each connection and passes this information backward layer by layer. Each connection gets assigned its share of the error. The network then knows which weights to adjust and by how much. Connections most responsible for the error are changed the most. All weights are updated, nudging the network toward better guesses. This completes one learning cycle: guess, measure, error, update. Repeating this process is how the network learns. This cycle, forward pass, error calculation, backpropagation, is repeated thousands or millions of times. Each time the network makes tiny adjustments, slowly becoming more accurate. Backpropagation is the core algorithm that made deep learning possible. It unlocked the power of networks with many layers, enabling today's advanced AI. From facial recognition to language translation, backpropagation trains the systems we use every day. Without it, AI wouldn't be the transformative force it is now. It's a simple idea: learning from mistakes, expressed in math, powering the most complex technology we have. That's the beauty behind the brains of modern AI.